Alright, so now let's look at some practice problems involving intermolecular forces. There's a couple different ways you can see these questions asked. I'll run through a few of them just to give you an idea of what you're going to see when you get asked about these questions. And ultimately, a lot of intermolecular force questions come down to comparing the strength of intermolecular forces. Also, you'll see some questions where you have to list the intermolecular forces that exist between either identical molecules or different molecules. So we'll look at each of those in those cases, and also we'll look a little bit at being able to identify if a molecule is polar or not. So in the few examples where we have polar molecules, I'll be sure to point out how you can tell that they're polar. So without further ado, let's get started with this first question. And this first question asks us, for each of the following molecules, list all the intermolecular forces they would experience with identical molecules in the liquid state. So basically, we're going to see a series of molecules, and we'll go through for each molecule and say, okay, what intermolecular forces is it going to have with other identical molecules to itself? So let's have a look at some of those. Got them here. Okay, copy and paste. So let's start with this first one right here. So for this first molecule, if you're getting pretty good at your line structures, or if you just watch a lot of my videos, because I talk about this guy a lot, this is butane, right? It's got 4 carbons and 10 hydrogens. So we would consider this molecule to be a hydrocarbon. You know, if you just see lines going up and down, you got a hydrocarbon. And what do you know about hydrocarbons? What is the only intermolecular force hydrocarbons can have? If you said London forces, you would be correct. So I will put, let's go ahead and label this guy London, because those are the only forces that this molecule is going to have. I apologize if you can hear my clock in the background. So the only forces for this molecule will be London. Moving on to this is also kind of similar to butane. It's butanone. So it's a ketone made from butane, basically. So what we want to know is, what forces is this going to have with other butanone molecules? Well, we know right off the bat it's going to have London forces, because all molecules have London forces. London forces are basically the default type of intermolecular force. So we know right off the bat it's going to have London forces. So you can automatically put that for any covalent molecule. So let's see. Now we have to determine if we can do the other types of bonding. Well, the other types of intermolecular forces, I should say. So what we need to identify next is this a polar molecule? So to determine if this is a polar molecule, the first thing you need to do is determine if there are any bond dipoles. So remember, you have a bond dipole whenever you have 2 elements that are bonded together, covalent elements, that have a high degree of electronegativity. So they are highly different in their electronegativities. So down here at the bottom of the molecule, these are just carbons and hydrogens. So this is a carbon bonded to hydrogens, this is a carbon bonded to hydrogens, this is a carbon bonded to hydrogens. There's no electronegative difference between carbon and hydrogen. That's important. I would keep that in mind. But we do have this carbon right here double bonded to this oxygen. And there is going to be a bond dipole right here. Okay? So yes, this is a polar moment on this molecule. The question is this a molecular dipole? Is it true for the whole molecule? Well, we only have this one bond dipole, and it's pointing in the up direction. And the molecule is pretty small, so this oxygen is having a pretty decent polar influence over this molecule. So yeah, I would go ahead and say this forms a molecular dipole. You know, if we had more carbons attached to this going off like that in a bigger chain, then I wouldn't be so quick to call this polar. But since this molecule is pretty small, and we have that one bond dipole sticking up, I think we're okay to call this polar. So if we know that this molecule is polar, we know that it's going to form dipole-dipole forces with other butanone molecules. So because this molecule is polar, it will exhibit dipole-dipole forces like that. So I'm going to shorten dipole-dipole by just saying dipole. We don't have any hydrogen bonding for this molecule because there are no hydrogen donors. We have acceptors, so we do have lone pairs on this oxygen that can act as a hydrogen bonding acceptor, but we have no hydrogen bonding donors. So ultimately no hydrogen bonding can happen between identical molecules of this, so we only have London forces and dipole-dipole forces for this particular butanone molecule. So now let's move on to carbon dioxide, CO2. So the first thing you need to do if you see a molecular formula is draw the Lewis structure, because the Lewis structure is going to be able to tell you a lot about what type of forces this particular molecule can have. So what I would do if I were you, I would go ahead and pause the video really quick. See if you can draw the Lewis structure for CO2. Hopefully you're getting decent at that. You should be. And unpause it to see if you were correct. So here you go. Here's your Lewis structure for carbon dioxide. And I mean, if you paused or didn't pause video, I don't really care either way, just to let you know. But it's just a helpful hint. So here's our Lewis structure. So we know right off the bat that we're going to have London forces for carbon dioxide, because all molecules, all covalent molecules have London forces. Right? So we know that we have our London forces. So the question is, do we have dipole-dipole forces? Is this a polar molecule? Well, the first thing you need to do is draw your bond dipoles. See if you can identify where the bond dipoles are going to be on this molecule. So you got one coming over here to this oxygen. That's a big arrow, sorry about that. And sometimes the mouse gets out of control. And here's another dipole right here. So we've got two dipoles going to both of the oxygens. The question is, are these bond dipoles pointing in the same direction? Pretty clear that they aren't, right? They're pointing in opposite directions, which means we do not have a molecular dipole, which means this molecule is not polar. So ultimately, this will not be able to participate in dipole-dipole bonding because it's not polar. Also, CO2 won't be able to do hydrogen bonding because there's no hydrogen bond donor in this molecule. So with identical CO2 molecules, it cannot do hydrogen bonding. It has acceptors with these lone pairs, but it does not have any donors to hydrogen bond with itself. So the only forces we're going to see between identical CO2 molecules is London forces. So now let's move over here to the ammonia molecule, NH3. And what we're going to see with NH3 is something interesting. So go ahead, see if you can draw the Lewis structure for NH3, see what you get, and see if you can find any bond dipoles. See if you can predict the polarity of NH3 while you're drawing it. And then you can unpause, see what you're going. Unpause the video, see where you're at. Okay, so I went ahead and drew the Lewis structure. Hopefully yours looks like this too. And I went ahead and said that we have London forces because we automatically know that we have London forces for this. So the question is, do we have a molecular dipole? Do we have polarity in this molecule? Well, we're going to have bond dipoles on each of these hydrogens going to the nitrogen, because nitrogen is part of Funkel-Bryce. It's very electronegative. So there's going to be bond dipoles coming off of each of the hydrogens going to the nitrogen. The question is, are these bond dipoles all pointing in the same direction? Yeah, because you have this lone pair on top of the nitrogen that's pushing those hydrogen bonds down, making that trigonal pyramidal shape. And because of that trigonal pyramidal geometry, that's why geometry is important when you're looking at polarity. Because of that geometry, all of those dipoles are pointing up. And because all those dipoles are pointing up, we can say that we have a molecular dipole in the up direction, which means this is a polar molecule. Because NH3 is polar, we can say that it participates with dipole-dipole forces between identical NH3 molecules. Okay, so we've established that it has London forces, and we've established that it has dipole-dipole forces. Last question we have is, does this molecule have hydrogen bonding? So we need to look for the two requirements for hydrogen bonding. You have to have a hydrogen bonding donor and you have to have a hydrogen bonding acceptor. And remember that your donor is going to be a hydrogen that's bonded to oxygen, nitrogen, or fluorine. If you have a hydrogen but it's not bonded to those three elements, then you don't have a donor. But you do have a donor if it is bonded to those three elements. So let's look. We absolutely have donors up here. We have three of them, technically, because each of these hydrogens is bonded to a nitrogen. So each of these hydrogens could act as a hydrogen bonding donor. Right? But we'll pick on just one for the sake here. So, do we have a hydrogen bond acceptor? And I think the easiest way to show this would be to draw a second ammonia molecule, because if you draw a second ammonia molecule, you can see if they're able to have that hydrogen bond with each other by drawing it. Okay, so what I've done here is I've drawn an identical ammonia molecule over here. I've drawn it sort of upside down though. And so we see that we have our donor with this hydrogen here. And remember, your acceptor, a hydrogen bonding acceptor, is going to be a lone pair on nitrogen, oxygen, or fluorine. So you'll see we have an acceptor right here, which means they form hydrogen bonding with each other, because you have an acceptor on this molecule and you have a donor on this molecule. So we can say that NH3 is going to have hydrogen bonding because we have both of the requirements for hydrogen bonding. So we can go ahead and chalk up, and then ammonia is pretty cool because it has all three. And there are quite a few molecules that have all three types of forces, right? We got London dipole and hydrogen. So ammonia is a pretty universal solvent. Not quite as much as water, but ammonia gets around pretty well by itself. So now let's look at this next to last guy over here, Br2. This one's pretty simple. So Br2, draw your Lewis structure, right? So Br2 is just diatomic bromine. It's elemental bromine. So draw it like that, and you got your lone pairs that go around it. Like that. So ultimately, what do we have here? Well, we know that we have London forces. Alright, so no question about the London forces. What about dipole-dipole? Well, bromine is part of Funkelbrice, but there's no dipole here because bromine is just bonded to another bromine, which means we have equal electronegativity between the two bromines. So no bond dipole here, which means no molecular dipole, so no dipole-dipole forces for the bromine molecule. And also no hydrogen bonding because we have no requirements here for hydrogen bonding. So ultimately, this bromine molecule is only going to have London forces. It will, however, have pretty decently strong London forces with other bromine molecules, but nonetheless, it only has London forces. So let's look now at this ethanol molecule right here, CH3CH2OH. And we're going to try to decide, is this what forces are going on with this molecule here, I should say. So, of course, we know it's got London. Alright. Now, the question is it polar? Well, do we have a bond dipole? We do. We have a bond dipole going toward the oxygen, right? Because you got the carbon to oxygen. You'll also have one coming off of the hydrogen, but I'm not going to worry about that so much. I'm more worried about the carbon to oxygen dipole. So yeah, overall I would say this molecule is polar. But this is going to be similar to the butanone. The more carbon and hydrogen lines you draw onto this, so if you kept going with the up and down peaks in the chain structure, ultimately you would lose a lot of your polarity. Because this molecule is small, you only have 2 carbons bonded to the oxygen. So yeah, I would say this has a molecular dipole. But if you started adding more carbons to this chain, you would end up losing your polarity at some point, where the the chain structure of the molecule would override the polar part of the molecule as far as molecular polarity goes. Although there will always be a polar influence going on with this oxygen. It's just that that polar influence would go down with the more up and down peaks you add to this alcohol. So yeah, we'll say it's polar, which means it will have dipole-dipole forces. So we know we have London, we know we have dipole-dipole. The last question is, do we have hydrogen bonding? And to answer that question, I've kind of modified the Lewis structure a little bit to give you a little more to look at. So does it meet the requirements for hydrogen bonding? So we have a bonding donor here, right? This hydrogen is bonded to the oxygen. So this can act as a hydrogen bonding donor. And do we have an acceptor? Yeah, because we have lone pairs. We have 2 lone pairs on the oxygen. So these lone pairs can act as hydrogen bonding acceptors. So we have a donor, we have an acceptor, therefore we can undergo hydrogen bonding with this ethanol molecule. So we have all 3 here. We also have a trifecta for the ethanol molecule where we have London, dipole forces, and hydrogen bonding. So that's how you can go through molecules and identify what type of forces they have. Now let's do a little practice with comparing molecules to see how they compare based on strength. Okay, so in this next series of questions, we want to look at each pair of molecules and predict which would have a higher boiling point. So this is interesting, where in many cases, not all cases, but in a lot of cases, you can predict which kind of substance would have a higher boiling point based on if it has stronger intermolecular forces. Because ultimately, the stronger your intermolecular forces, the higher your boiling point would be at the liquid state. And that's because, ultimately, intermolecular forces will affect how those molecules are interacting with each other. So if you've got a liquid of molecules, of the same molecule, identical molecules, the stronger the forces there are between those molecules, the more energy it's going to take, the more thermal energy, which is heat, it's going to take to pull them apart. So that's why you see boiling point increase with the strength of your intermolecular forces. So the stronger your forces, the higher your boiling point. So let's look at each of these. So up here, the first head-to-head battle is between acetone and water. So what you want to do when you're comparing these is look at what forces they have, right? So for acetone, we're definitely going to have London forces. We're also going to have dipole-dipole forces because this is a polar molecule. And we're going to have that is the question, do we have hydrogen bonding? We don't, because we don't have any of the requirements here for hydrogen bonding. So we can do London, we can do dipole-dipole, but we can't do hydrogen. For the water molecule, we know we can do London. Water is very polar, so water can definitely do dipole-dipole. And water can do hydrogen bonding because it's got both requirements for hydrogen bonding. So ultimately, water has the strongest intermolecular forces between its identical molecules. So water would definitely have the higher boiling point by quite a lot. Water has about twice as high a boiling point compared to acetone. So water wins in this head-to-head. Water would have the higher boiling point. So now we're comparing propane, which is this molecule here, with pentane, which is this molecule here. So we know that both of these are hydrocarbons, so the only forces that exist between these two are London forces. The question is, which of these has the stronger London forces? So which of these has the strongest London force? That's going to let you know which has the higher boiling point. Well, remember, with London forces increase with your number of electrons. So the more electrons your molecule has, the stronger your London forces. So we know that pentane has more elements than propane, right? It's a bigger molecule. That means that pentane is going to have more electrons. If you have more atoms, you also have more electrons. So in this case, pentane is going to win this head-to-head battle by quite a lot, actually. The boiling point for propane is negative 42 degrees Celsius, whereas the boiling point for pentane is 36 degrees Celsius. So a huge difference between pentane and propane in terms of their boiling points. Pentane clearly has the higher boiling point. So now let's look at CH3F versus CH3I. So we know both of these are going to have London forces. We know that they aren't going to have hydrogen bonding because neither one of these meets the requirements for hydrogen bonding with identical molecules. So are both of these molecules polar? Yes, because both of them, if we were to draw the Lewis structures for this, we would have this would be the Lewis structure for this guy, and this would be the Lewis structure for this guy. So we have a carbon to fluorine and a carbon to iodine bond, respectively, and there is a bond dipole there, and there is a molecular dipole there, especially for CH3F. There's a very big dipole there. So both of these are polar. The question is, which of these is going to have a stronger polarity? And I kind of just answered that a second ago. It's going to be this guy. And the reason it's this guy is because it's bonded to a fluorine. Fluorine is more electronegative, which means it's going to have a bigger dipole than CH3I. So if you're comparing these two, fluorine is much more electronegative. It has a much more prominent molecular dipole, which means it's going to be more polar. More polar means stronger dipole-dipole forces. This guy would have the higher boiling point than this guy, based on the stronger dipole-dipole interactions. And then finally, let's compare these two down here. So we're looking at this ethylamine molecule here compared to this dimethyl ether molecule here. So we know both of these are going to have London forces. You could argue that, yeah, both of them are polar. Dimethyl ether is definitely polar. Ethylamine is, yeah, I would argue that it's polar. But ethylamine is going to win because it can do hydrogen bonding. So it meets both requirements for hydrogen bonding. Dimethyl ether cannot do hydrogen bonding. So no luck here for dimethyl ether. Dimethyl ether has a very low boiling point, actually, whereas ethylamine is going to have the higher boiling point of the two. So let's look at one last example, and this is probably the last type of question I could see you potentially being asked. And that is, what intermolecular forces could exist between two different molecules? So we looked at what would exist between identical molecules. Now let's look at one quick example of if they were the same. Sorry, if they were different molecules, rather. So here I've got a water molecule here and a dimethyl ether molecule here, right? And we've already established that water can do hydrogen bonding, and we've established that dimethyl ether can not do hydrogen bonding. However, both of these molecules are polar. The question, though, is what kind of forces exist between each other? So not identical molecules, but each other. So really the question here is, can both of these molecules, when you put them together, form hydrogen bonds? And the answer to that is yes. And that's because water can give us the hydrogen bonding donor right here, right? Because we have this hydrogen bonded to the oxygen that can act as a donor. And we have an available lone pair on oxygen on the dimethyl ether. We've actually got two lone pairs. So if we were to take that lone pair there, right, we can form our hydrogen bond between the lone pair on the dimethyl ether and the hydrogen on the bonded to the oxygen of the water. So that's the thing. When you have different types of molecules, oftentimes they can form intermolecular forces with each other that they can't form with identical molecules of themselves. So dimethyl ether on its own can't do hydrogen bonding, but if you put it with a substance that has a donor, then it can form that hydrogen bond. So that's just a quick example of what that would look like. Hopefully this clears up a lot of issues you might have had with intermolecular forces, and hopefully this gave you some good practice on how to approach these problems. And this is the last video of the semester, so celebration time.